Okay. So we will have, let's start our plate analysis. So like I said, we will have a plate which is a structure like this, which will have some perpendicular loading to the plane of the plate. Okay? So what is going to happen is this loading. Okay, so imagine this plate is simply supported on this edge, for example. So we always have to have what we call boundary conditions, and is also supported on that other opposite edge. Okay? Okay, we have something like this, and is also supported on this edge here. Because if we don't have any support, so this comes a bit from what you learned in statics in year 1. By the way, you did statics with me or was with me? Okay. And then what is going to happen with this plate is it is going to deform something like this, right? Of course, I am exaggerating you see this blue deformed surface, so I am exaggerating the magnitude of this, what we call deflection, this vertical displacement. So if I put here a coordinate system, let's say X, Y, and Z, so this plate, so assuming this load is a force in the Z direction, what is going to happen is this plate will have a displacement in the Z direction only, right? It's what is called the transverse displacement, or also known as deflection. So when we talk about deflection, you know is a displacement in the perpendicular direction to the plate. Okay, so what we are going to do is I'm going to look at the plate from this side view, okay? And then what I will have is going to be a cross section. Okay? You will have the neutral surface is equivalent to what you learned in beams. We did beams in year 1, right? Remember the neutral axis? The axis where the stresses are equal to 0. The bending stress equal to 0, right? So you have a similar thing in plates. And then after applying a load, the plate will deflect, or if you want, the plate will, so let me zoom in, go to this configuration here in red. Okay? And we will say that this angle here, we will call it alpha. And then if I say, okay, this is my Z direction, initial Z direction, this is going to be my X direction, okay? So if I do this, connect these points with this angle here is also going to be the same alpha. The reason is this is perpendicular to this, and this blue is perpendicular to this blue, so this angle needs to be the same. Right? And I will say, okay, so if you look at this point here, this corner on the initial plate in blue, it will go from this position to this position here, right? Yeah? After the plate's deflection. So I'm going to say this little bit here is going to be dW. W is the displacement in the Z direction, okay? So typically we use this. U is the displacement along X. V, we used to say this displacement along my y-axis, and W, displacement along Z, okay? It doesn't have to be like this, but if you pick most of, stress analysis, stress strain analysis books, plates, shells, stress structures, typically this is the convention. So when you see V, U, W, you know what that represents, right? And then we can also say another thing in this figure, that this little bit here from here to here is going to be, so let me move this guy too. So this is going to be dx, because this is basically is an increment in the x direction. Why am I doing this? Because now I can say, if I look at this rectangle here, let me try to, if I do this, if I look at this rectangle, I will have something like this. dW, dx, and this is alpha. Okay? Then I can say the tangent of alpha is going to be equal to dW dx, right? Basic trigonometry. And this, basically this is a slope, isn't it? And this slope is negative. Yeah, so if you have a function like this, if you have a slope like this is negative. If you have something like this is positive slope, right? Yeah? Yes?
Negative because the red color one is down.
No, negative because the slope is this, right? This is the slope. And like I'm saying here, negative, right? Okay. So I can leave it here. So this is the slope, because it's something we are going to use a lot to impose boundary conditions in plates. So slope is a kind of a rotation. Imagine that point. Imagine you are in this plate here configuration with this support in this edge, right? So the plate is going to be allowed to rotate about this point, isn't it? So about this point here in the edge, the plate is about to rotate. So you mean the slope here is different from 0, isn't it? There is a slope there. So we can say the slope, we can associate it to a rotation. And this is important. For example, if you have a plate that is clamped, the rotation should be equal to 0 at that point. Rotation is constrained. Something you are going to do a lot in FEA, in Abacus. Okay? Impose boundary conditions in Abacus. So you need to know what kind of boundary conditions you are going to impose. Is the plate simply supported? Yes. So it means rotation at the boundary condition, rotation is allowed. Is the plate clamped at an edge, for example? So the rotation is constrained, should be equal to 0. And then in Abacus you need to say, okay, this edge of my plate is going to be clamped, so I'm going to constrain the rotations about that direction, right? Okay? Now, let me copy this and put in a copy. Let's see if I can put it here. Good. And let me clean a little bit this thing now, because we are going to look to this setup here from a different perspective. So let me if it's easier to do like this. Okay. So, I'm going to say, so for example, if I look at this point, it will go from here to here, I will say, and this is my displacement in the x direction, u, and this is my, so this point, starting from the neutral axis, this point is at a distance z from neutral axis, okay? So don't forget, this is our coordinate system, x, z, so x is the horizontal direction, so the displacement along the horizontal direction is u, and this point along the thickness of the plate, which is the z direction, the transverse direction, is located at a coordinate z, that location z, okay? And then I can say now that tangent of alpha, which is the same alpha we defined before, now is going to be equal to u over z. Okay? Or if you want, I can say that u is going to be equal to z times tangent of alpha. And, oh, what happened here? And what I can do now is replace this tangent of alpha here, and then I will get something like u is going to be equal to minus z dw dx. Okay? All right, so what I've been doing so far is nothing more than just using trigonometry, right? The concept, a tangent of angle. I didn't do anything more like that. I'm just applying that on the two different configurations of the plate. One is the blue, is the initial configuration. The other is after loading being applied, so it's going to rotate, to deflect, right? Is the configuration in red. And what I'm then doing is I'm getting some geometric relations, which this relation here is quite important. Why? Because you can see now that there is some relation between the vertical displacement W and the horizontal displacement U. Okay? Yes?
Slope doesn't look like it's going down.
Sorry, can you speak a bit louder?
Slope doesn't really look like it's going down.
This slope here. Yeah, that's why you have plus here, positive, not negative. Yeah? Okay? So basically, following your question, so in this first case we derived, we were looking at this triangle, like this triangle here at the top. So the slope is negative, right? While for the second analysis here below, the triangle we are looking is this one. And slope here is positive, right? That's why you have here plus, not minus. Okay? Yes?
So if we look in the other direction, would it be, you would end up with the same answer, u equals z?
Yeah. So basically what your colleague here is saying is that if instead of x we are looking at the y axis, right? Yeah, so you will have here, instead of u, you will have v, still z. But then here, instead of x, you will have y. Okay? Then everything else will be the same. Yeah, is a very good point. Okay? All right. So let's continue. Let me just copy this to a new page. Let's put this one here. Please remind me, okay, let's see, what time is it? In 10 minutes to do a 5 minutes break, okay? We need to do some breaks. Yes?
So you upload this right in the right system.
I have many things from previous year. I will upload everything I have. Yeah, this is being recorded as well.
Oh, this is
Yeah, you can see here at the top. The time is counting is recording, right? Okay? All right. Now, next step is, okay, so we have calculated the displacement field of a plate. Now I'm going to move to the strain field. Okay, yeah, I can put like this, strains now. And we are going to start with, okay, strain in the x direction. Okay? So, you know, definition of the strain is 1 over 2. The derivative of the displacement in the x direction in order to x plus same thing. So this is basically equal to du dx. Okay? So, what am I going to do? I'm just going to derive or replace my displacement u we calculated before. Basically, I'm going to derive again in order to x. So then you get something like this. So minus z. Instead now of derivative of w, I have the second derivative of w in order to x. So this is going to be equal to, I'm going to give this definition here. So this kx is going to be equal to the second derivative of the deflection in order to x. This is known as the curvature. Curvature of the plate. So basically, we can say, okay, dw dx is the slope of the plate, or is the rotation of the plate. D square dx square is the curvature. Okay? Well, and this, I think, is good to understand these two things. So, like I said, rotation is something like this. Imagine, this is a flat plate that I'm holding here in my hand, right? These sheets of paper, right? If I just rotate the plate, and if it remains flat after rotation, my curvature is going to be equal to 0. No curvature, right? But if it deflects like this, you can see some curvature here, right? You need to have a radius. Curvature is the inverse of the radius, right? Okay, I'll give you another example. A flat plate has an infinite radius, right? Maybe I can use this. So imagine you have a flat plate like this. So this plate will have a radius which is equal to infinite. It's flat, right? So the curvature is the inverse of the radius. So if the radius is infinite, the curvature of a flat plate is going to be 1 over infinite is equal to 0, right? No curvature. Now, if instead of a flat plate you have a plate like this, so this will have a radius r, which is a finite radius. So the curvature of this guy is going to be second derivative. So of course, if this is my x direction, and if this is my z direction, it's going to be 1 over r. Okay? So, slope and curvature, different things. I hope you understand what are the difference between these two guys. But one good conclusion is our strain, so when we load a plate, we get a strain which depends on two parameters, basically. One is the distance z from the neutral axis, or the neutral plane of the plate, right? Same thing like in beams. Look, if you have a plate like this, the neutral plane is this one, so your z starts counting from this plane, right? So the strain at the neutral plane is going to be equal to 0 because z in this equation is going to be equal to 0, right? So strain equal to 0. But then once you start moving along the thickness direction, your strain starts to increase with z. Similar like what was happening with the beams, remember? So, like I was saying, strain depends on two parameters. One is z, the distance to the neutral axis along the thickness direction. The other is the curvature. Okay? So in a similar way, we can say that if you do the same analysis for the y direction, you will get to this conclusion. Now the curvature along the y direction, and this curvature is going to be equal to the second derivative of the deflection in order now to y, not x. Okay? Now, what about the shear strains? By the way, one thing I didn't say in the introduction to this model about the stress. We are going to, so stress and strain concepts you learn in year 2 are going to be very important for this model, okay? So my advice is do a review what you learn in year 2, stress, strain, transformations between coordinate systems, yeah? What is a linear strain, what is a shear strain, what is a shear stress, what is a direct stress or normal stress, okay? Principal stresses, principal directions, these kind of things are going to be important. So I advise to do some review, okay? And also, of course, if you are not following what I'm saying, please interrupt me, okay? Or if I'm going too fast, interrupt me as well. Now, shear strain, epsilon xy, by definition is given by 1/2 derivative of the displacement in the x direction over the y plus derivative of displacement in the y direction over the x. Okay? So, there's another way you can represent the shear deformation. Okay, which is just a multiplication by 2, nothing special here. Okay, and then what I'm going to do is I'm going now to replace u and v in this equation. So we derived u and v. So maybe we can bring them to here. So let me copy this. Let me put it here. And then v is going to be equal to minus z dw dy. Okay? And then we can just replace, and then we will get the shear strain is going to be equal to minus z, second derivative of w dy dx, plus second derivative of w dx dy. Okay? So we can, so this is equal to this. So we can say this is going to be equal to minus 2z times second derivative of w dx dy, or this is going to be minus 2z kxy. So kxy is a kind of twist, right? Because shear basically is a distortion, isn't it? Shear is a distortion, right? So this k, I'm going to write here kind of a twist of the plate. Okay? So we have the strains the derivation of strains, so I can summarize all the strains in this slide here. So we have this one, we have this one here, okay, minus ZQI, and then we have the shear strain. Okay, so the strain field for a plate was also derived at this point. So we're going to do now a 5 minutes break, and then we will come back and continue from this point, okay? So it is 10:09, so we come back at 15, so 6 minutes. All right, see you soon. All right, so I just wrote here. What is this that I just wrote here? Anyone recognize it or not? Yeah. Yeah, G is the shear models, yeah. Or rigidity models as well. But these equations I wrote there while you at the break. What are they? Anyone recognize these equations? What do you have on the left-hand side of these equations? Strain. On the right-hand side? What do you have on the left? Oh, on the right-hand side. Huh?
Is it the strain in different axes?
No. Axes are the same. X, Y, and Z. What do you have on the... Okay, let's look this. What is this? Young's modulus. What is this? Poisson's ratio. What is this? Sigma XX. Stress. Direct stress, right? In the X direction. Direct stress in the Y direction. Direct stress in Z direction, okay? So, this is what is known as the Hooke's law. Which relates stresses with strains and vice versa, right? And that relation is done through these material parameters, which are the Young modulus and Poisson's ratio. So, if you know the strains, you can get the stresses from the Hooke's law. Or if you know the stresses, you can get the strains. So far, what we have been doing for plates is we have been deriving the geometric relations or the kinematics. So we derive the strains in a plate. So if we know the material properties, the Young modulus Poisson ratio of the material you are using in your plate, we will be able to calculate the stresses from these equations, right? That's what we're going to do. And why do we need to know the stresses in a plate? Well, if you want to design, for example, this building, this floor, for example, we are all in, right? We are all in. So our weight is the load, right? the weight of this desk, chairs, the weight that comes from the floors above in this building, all of this is transferred to this floor. This floor is a plate. So if you are designing this floor, you need to make sure this floor can carry the loads that it is designed for, isn't it? How do we do that? Well, we need to calculate for the loading that we have, we need to calculate the stresses. Okay? And what do we do with the stresses? Well, what we do with the stresses is, okay, you know the material you are using, because then you go to the lab and you do a tensile test, for example. So you all know these things, right? Elastic domain. This is the yield stress of the material. After this point, you go into the plastic domain. So we don't want to go into the plastic domain because, for example, if you go to this point in the plastic domain, when you unload, you will have a permanent deformation on your plate. You don't want that, right? Imagine you come to this lecture room, just your weight will induce a permanent deformation in the floor. So then you come tomorrow, after a couple of weeks, this does not look like a room anymore. So we don't want that to happen, right? So we need to make sure that the stresses we have installed in our plate, the stresses that come from this equation here, we need to make sure they are below the yield strength of the material. If they are below, it means what? The material you use is able to carry that load. It's not the rack. Right? Sorry. If it is above, it means the material does not have enough strength, right, to carry that load and remain in the elastic domain. We want to remain in the elastic domain. The reason is, if we load from 0 to this point, and if we unload, we always come parallel to the elastic domain, right? So we come back to 0 in terms of strains. So no permanent strain in the material. So from this figure here, I can tell you another thing. The slope of this elastic domain, the slope is the Young modulus. So you measure the Young modulus by getting the slope of this line in the elastic domain. Right. So let's come to these equations here. There's one, I will say, assumption we do in thin plates. Okay, we are going to consider for thin plates plane stress. Which means the stress, the direct stress along the thickness direction, we are going to consider. So typically it is very close to 0. We are going to assume is exactly equal to 0 for the analysis. So this term here equal to 0, equal to 0. And this is even closer to 0 when the thickness becomes close to 0 as well, right? So if you have a very thick plate, that assumption might be a bit wrong, but for thin plates, that assumption is very accurate, okay? Yes?
I was going to put, how did you get the X and Y? Like, how did you get that?
Oh, this is the Hooke's law. Okay, Hooke's law. Right?
Is this 2D or 3D?
Well, I start with 3D because you can see here stresses in the 3 directions, in X, Y, and Z direction, stresses, right? But then, that's why I'm now saying, so I'm going to make now, basically going to plane stress. Basically, I'm going to 2D now, stress, okay? In this case, I'm going to say my sigma zz equal to 0. And then from these equations here, you can solve now these equations for sigma x, sigma y, with that assumption in mind. And then you get something like this. Sigma xx is going to be equal to Young modulus 1 minus Poisson ratio square times the strain in the x direction plus Poisson times the y in the stress direction. So this comes automatically from the solution of Hooke's law, solution or solving Hooke's law in order to the stresses. Okay? And this one is quite easy. Right. Now, we can replace the strains because we derived the strains for plate. And then we get something like this. We have here the curvature in the x direction plus Poisson ratio times the curvature in the y direction. And for this one here, we have similar. But this we just swap this qy and qx. Okay? And for the shear strain, so basically what we have now, after using Hooke's law, what we have now is the stresses, sigma x, sigma y, tau xy is the shear stress, function of material properties, Young modulus and Poisson ratio, and function of the curvatures of the plate, right? So one more thing you can do here is if you use the rigidity modulus equal to Young modulus over 2, 1 plus nu, and replace, you will get something like minus Ez 1 plus Poisson ratio times Qxy. Okay? All right. So we are making some progress. We started from simple deflection of the plate. We derived the displacement field. We derived then the strain field. And now, with the Hooke's law, we get the stresses in the plate, which is great. But what we need to know now is, how do these stresses evolve or progress from one point to another in the plate, right? So I'm quite sure you know that when you did learn stresses in year 2, you are doing the analysis for stresses at one point of your body, right? But the stresses, they can be different points of the body. So this is, for example, imagine you have a cube like a cube. You apply, for example, one force, let's say 10 kilonewtons here. You apply a pressure in this area, pressure of 100 MPa, for example. So what is going to happen is, if you are looking at, okay, so let me draw this. If you are looking at this point, you might have here a sigma xx, sigma yy, tau xy. which is going, if you are looking at this point here, for example, you are going to have a different so this and this, they are going to be different. Right? So this is in fact something you are going to see in Abacus, in FEA, in Computer Lab, when we are going to do an analysis of what you are going to see a distribution of the stresses. This color scheme, you have learned in ANSYS, right? Color scheme, you have a scale which tell, okay, the cold colors, they usually are the low values. The hot colors, like yellow, then going to orange, then red, right? So this is highest values, okay? So you have then this color scheme distribution in the body, so you can see for all points in your body what are the stresses in all points, the stress distribution, right? So we need to know for plates how these stresses are going to be distributed in the plate. And then what we are going to do is we are going to let's see if I can draw it properly here. So I'm going to exaggerate here the thickness of the plate, going to make a bit too big, but it's good for visualization purposes. So you will have the neutral surface of the plate, something like this. So the coordinate system is going to be, so let's put here a coordinate system, something like this. You always need to have a so this is going to be my x direction of the plate, y direction, z direction. Okay? And then what I'm going to do is I'm going to look at a tiny, tiny infinitesimal element. This one here. So this element, so let me put it here a bit bigger. So this element will have, so this distance is going to be dy. This distance is going to be dz. Okay? So, you know, infinitesimal analysis. So what we do is we get an infinitesimal element. And then what is going to happen is, in this infinitesimal element, which can be a point in my plate, right? I can represent a point like being an infinitesimal element like this. So basically these dy, dz are very, very low values. And then in this point what I'm going to have is my stress sigma xx. Okay? So this stress, I don't know if you remember from stress analysis, you did in year 2. Why do we call this sigma xx? Just a quick refresh. The first subscript is related to the normal, to the plane. Okay? So the plane is this y plane, this cross section of my plate. And the normal to this plane is my x-axis, isn't it? The normal to this plane is my x-axis. Okay? That's why the first subscript is x. The second subscript is the direction of the stress vector. So this vector has the direction of x. So the second subscript is x. Okay? Right. So another thing I need to include here is, okay, let's say this is going to be half of the thickness. Let's say thickness is t over 2. This is going to be the other half. Of course, I'm saying here the neutral surface is at the distance between the top and bottom surfaces of the plate. And then I can say that this point is at a distance z from the neutral axis. Okay? And then look at this. I can also say this infinitesimal element as an area, dA, which I can say is equal to dy times dz. You all agree? I can say this, right? So if I multiply my stress by the area of this infinitesimal element, so, you know, stress is a force divided by an area, right? By definition, okay? So if I multiply the area by the stress, I get a force, right? So that's what's happening here. This is going to be a force, which I will say dF, because we are talking about infinitesimal values, right? So don't forget, this stress, sigma x, is acting on this infinitesimal element with area dA. So this will give me a force, which is going to be a tiny, tiny force, right? Eventually, I don't know. But anyway, we are working on infinitesimal. We are doing infinitesimal analysis, so dF. Now, I can write this. dA is equal to dF dy, dx dy. What if now I multiply this dF by z? So what if I do this? dF multiplied by z. What do I get? Yeah. No, but the force times the distance in the perpendicular direction gives me what? A moment. Yeah? So, yeah, this is going to be a moment. So if I do this, if I replace dF by what I have there, sigma xx dx dy, okay? I can say this is going to be infinitesimal contribution to a moment, and that moment is going to be along the x direction. Okay? Basically, it's going to be a moment like this. I'm going to try to represent here in red. Okay? Now, what I'm going to do is I'm going to integrate both sides of this equation in order to z. So I'm going to do the integral in the thickness direction. So the limits of my integral are going to be minus t over 2. So I'm going from this point here, minus t over 2, and integrate in this direction all the way until I get this point plus t over 2. These are the limits of my integral, right? Yes?
I have a question. In the area, you put dx by dy. Isn't it dy by theta?
Oh, yeah, you're right. Yeah, sorry. Yeah, you're absolutely right. Yeah, I have it right there, right? It is right here, but for some reason here I just... Okay, so this should be dz times dy, correct? It's correct, right? Okay, thank you. All right, so now the upper limit is t over 2, and then I'm going to be integrating everything I have on the left-hand side of this equation. And then, of course, I need to do the same for the right-hand side. And then I will have, I'm going to put like this. Okay, so I can say, let me copy this.
So,
Yeah.
should the z not be negative because it's going upwards, but in the coordinate system, the
So-
positive,
Sorry, can you speak a bit louder?
in the coordinate system, the positive z direction is down, but the distance z is going up, so should the z not be negative?
Yeah, it doesn't matter too much for this analysis. Okay. Okay, so this thing we are going to have. So this is going to be. So this integral is going to be my mx, and then I will have something like this. Okay, so I can say, can put like this. And this term here, I can write now here, this mx is going to be a moment per unit length This is known as stress resultant. I can put here moment per unit y length. Well, is not difficult to see from these two equations here, from this equation here. So basically, what I'm saying is this mx. So mx times dy. So this mx needs to be a moment per unit length in the y direction, so that when I multiply by dy, this cancels with this, and I get my total moment, right? Let's say mt. Let's put a t there just to see if it has. So this mx that comes from this equation here is an integration of the stress in the x direction along the thickness of the plate, but is a moment that is distributed, if you want, a moment that is distributed along the y direction. Okay, let's say is a something like this, a kind of a distributed load. Okay. So it's a moment per unit length. Okay, so you could do the same analysis again in the other direction. So I can summarize here the stress resultants. So let's put a title here, stress resultants. Okay, for the stress resultants we have stress resultant mx, Z sigma XX integration in Z direction. Stress resultant My is also the integration along the thickness. Z times sigma Y now. We have stress resultant for the twist moment, the torque eventually. Now you will also have Z, the distance to the neutral axis, but now this multiplies by the shear stress. Okay, this bit. So you know, the torsion is associated with shear, right? There's another thing that you typically is included in the stress resultants, which are the resultant forces. Going back to this figure here, maybe I can copy this. No, I don't need to copy. I don't have too much space. So what is happening is we are going to have in our plate, so I will try to make a smaller one here to see if everything fits. So if this is my X direction, if this is my Y direction, so I will have a transverse shear stress so this is a transverse shear stress, so it's a tau stress. Now the two subscripts, the first subscript, like I said, is the normal to the plane. So the normal to the plane continues to be plane X, perpendicular to X. So the first subscript is X. The second subscript is the direction of the stress, this vector in green. And that direction is Z. So tau X Z, transverse shear stress. Okay? It appears because we have forces in the transverse direction of the plate. We have another transverse shear stress, this one. So it's tau. The first subscript. Now this plane, the perpendicular direction to this plane is my Y direction. So this is going to be first subscript Y. Second subscript is the direction of that vector, which is Z direction. So this is going to be my tau Y Z. And then I can, if I integrate this over along the thickness direction, I get this other force resultants, if you want to call it that way. Force resultant about X is going to be the integral in the thickness of the transverse shear stress. The force resultant about the Y direction integral in the thickness of tau YZ now. Okay? Yeah, this makes the full stress resultants we need to work with. Okay? So just a little bit more. We are almost finishing the morning session, but I would like to finish with one more thing. And for that, let me just go back and copy these equations here. Maybe just this one. I know you are getting impatient now, but I think I'm a bit late with this. I'm being maybe a bit too slow, but I prefer slow and you to understand than quick and you don't understand anything. So hopefully is first case. Now what I'm going to do is I'm going to work out this stress resultant here. I'm going to copy this one. So you can see what is going to happen. I'm going to replace this stress here and integrate. Okay? And at the end we are going to obtain a very important relation you're going to see. So if I do that and I use this, basically this one is going to be here. If I do that, I get mx now we have here minus ez. Now this becomes, square, because I have z, because I have z multiplying z becomes z square over 1 minus 2, and then I have this thing, so let's keep this as it is. Okay? I'm just going to do a very simple primitive, which basically is going to be the primitive of z squared, which is going to be equal to z power 3 over 3, and this is going to be replaced on these limits, right? Right? That's the only thing I have to do. Everything else is constant in z direction. So if I do that, I get okay, so let me see. I will have here t power, if I do this primitive, t power 3, so 2 power 3 is 8, 3 times 8 is 24, minus with minus becomes plus, okay? Just a basic primitive. So we get something like this, minus e t power 3, 12, 1 minus Poisson ratio square, qx plus qy. Okay? And this guy here, I'm using a color scheme. Is what we are going to call D, is known as flexural stiffness. And this is equal to, this is a very important parameter. This is a very important parameter. Why? Because look at what's included in this parameter. Young models of material. Right? So higher the young models means stiffer your plate is going to be. What does that mean, stiffer? Stiffer means if I apply a load, if the plate is stiffer, it means it will get less deflection, less curvature. Right? What are the other parameters there? Well, Poisson ratio is, but the very, very important one is that one, t power 3. Thickness, exponent 3. A small increase in thickness in your plate, because it is power 3 there, will give a huge increase in the stiffness of the plate. Of course, that comes with a cost. More thickness, more weight. Right? So you start seeing some variables we are going to use on the design of us. So we are starting to get some conclusions. So this is what I mean about deriving things and understanding what is going on here. In this relation here, if you look at this equation here, maybe I can copy this equation to another slide. And we will end with this. We still have a couple of minutes, but just a little bit more. So, okay, I can write this equation like mx minus d qx plus qy. Look at this. This is very similar, like the Hooke's law I show you, right? Remember in Hooke's law, you had, on one side you had stresses, on the other side of the equation you had strains, and they were connected through Young modulus and Poisson ratio. Now here, on the left hand side you have a stress resultant, on this side here you have the curvatures, and here, connecting these two, what do you have? You have your flexural stiffness. And this is quite important because look at this. If I put these equations like this, qx plus nu qy, if I solve for this, for the curvatures, I get curvatures are going to be equal to the stress resultant, which is related with the load I apply to my plate, over the flexural stiffness. Goes into the denominator, right? So look at this. Higher stiffness of the plate, D, higher D means for the same load, less curvatures. Yeah? Or if you want to look at the other way around, is, okay, if I apply some curvature to my plane, if I impose some curvature to my plane, if I multiply that curvature by the stiffness of my plate, that will give me higher or lower stress resultant, which is related with stress, right? So the stiffness, flexural stiffness, this parameter is going to link these two things. One is the loading side and the stresses. The other is the curvatures or strains, right? So I think we should stop at this point. See you guys in 1 hour. So see you soon.